All right. So last week we talked about what a state function is, and we talked about some thermodynamic functions that are a state function. Similarly, entropy is also a state function, right? Meaning that the change in entropy of the system can be determined based on the difference between its final and initial states, right? And the path that we take between the initial and final states will not impact our change in entropy. So factors that influence entropy. I'm highlighting two here. They're not only these two, but these are two that we will focus on. One is the temperature of the substance. So in this left graph here, we have the fraction of molecules graphed against their kinetic energy, And we're told that temperature 2 is greater than temperature 1. So these are molecules at temperature 1, right? And we are graphing what their kinetic energy is against the fraction of molecules. Whoops. And then this is a graph of temperature 2, which is a higher temperature than temperature 1. And we see a more random distribution of kinetic energies for the higher temperature, right? So temperature is one factor that can influence the entropy, right? A higher temperature will increase the kinetic energy of those particles in the system and will result in a more random, more uniform distribution of those particles. The second factor is the phase of the substance, right? Whether it's in a solid, liquid, or a gas. So notice as we go from solid to liquid to gas, the entropy increases. The entropy increases. The molecules are, right? And we could also, if we think about this intuitively, if you think about like the microstates that these molecules are in, right? So this is for water. I think it's for water, going from solid, liquid to gas. So if we think about the microstates that the water molecules form in a solid versus a liquid versus a gas, we're going to see that the number of microstates will increase as we go from solid to liquid to gas, hence why the entropy increases. So let's talk about the second and third laws of thermodynamics. And remember, right, the system is the part of the universe that is of specific interest for our study. The surroundings is the rest of the universe outside of the system, but we usually, as chemists, only focus on the immediate surroundings because trying to take into account all of the surroundings is, I don't like using the word impossible, but it's much more manageable in an experimental context to focus on the immediate surroundings, right? But what I'm getting at is it's really challenging to measure surroundings in general, right? Measuring what's happening in a system is much more something we can accomplish in an experiment. So if we are correctly predicting the spontaneity of a process, right, which is the change in entropy of the universe, it requires that we look at entropy changes in both the system and the surroundings, So our change in entropy of the surroundings is directly proportional to the change in enthalpy of our system. Change in enthalpy of our system, delta H. It's inversely proportional to the temperature. It's inversely proportional to the temperature. This is of the surroundings, not the system, right? Change in entropy of the surroundings. Now, the second law states that all spontaneous changes causes an increase in the entropy of the universe. All spontaneous changes will result in an increase in the entropy of the universe. This is our second law of thermodynamics. So what that means is our change in entropy of the universe must be a positive value for spontaneous changes. So our delta S, or change in entropy of the universe, will be greater than 0 or a positive value for a spontaneous process. For a non-spontaneous process, it'll be less than 0. And at equilibrium, it will be equal to 0. Second law of thermodynamics. Now, the third law, and I briefly mentioned this earlier when talking about microstates. This law states that the entropy of a pure, perfect crystalline substance at 0 Kelvin is 0. And this is because all the molecular movement of the particles within that perfect crystalline substance has completely stopped. And it's only one possible way to arrange the molecules. So, if there's one possible way to arrange the molecules, what is the number of microstates for a perfect crystalline substance? This is me pausing. Correct. You all said 1. 1. So if we use our entropy equation, S equals K natural log of W, and we plug in 1 for W, we will see that delta S is equal to 0. Natural log of 1 is equal to 0. Third law of thermodynamics. All right. So just like with enthalpy, we can have standard enthalpy of formation values. We can also have standard entropy values. These are values that have been experimentally determined under standard conditions. And we have decided that the standard conditions are 1 mole of a substance at a pressure of 1 bar, temperature of 298 Kelvin, and for aqueous solution, it is at a concentration of 1 molarity. So we can use these standard entropy values, right, shown here to the right. They can be used to calculate the standard entropy change for a process. So how we calculate them, this is the formula. And the equation is similar to calculating the standard enthalpy of formation. That's what that little f is. So the standard, just like when we calculate the standard enthalpy change, we sum over the standard enthalpy of formation for all the products, and we subtract the sum of all of the standard enthalpy of formation of the reactants. And we similarly, if we're calculating standard entropy values. An important thing to remember is that you will multiply the standard entropies and standard enthalpies by the coefficients of the balanced equation. This is something we'll be doing in our discussion worksheet. And this is also something, problems you'll see in the book, because all of you are doing practice problems from the book, right? This is why, first step, we need to know what our balanced equation is for the chemical reaction that we're studying, because we're going to multiply that coefficient by each product and reactant when calculating standard entropy changes or standard enthalpy changes. All right, so remember, this is our second law of thermodynamics, right? Which takes into account the system and the surroundings to get the change in entropy of our universe. The fact that we take into account system and surroundings is a limitation of the second law, because measurements are seldom made on the surroundings, because how do we make measurements on the surroundings, right? When it's literally everything outside of our system. How can we, one, even define everything outside of our system accurately? And then it's challenging to make measurements on those surroundings. So they're seldom made on the surroundings. So this is a limitation of the second law of thermodynamics. To overcome this limitation, the question to think about is, what thermodynamic function focuses only on the system to predict spontaneity, right? So entropy looks at the system and the surroundings in predicting spontaneity. We want to introduce a function that focuses only on the system to predict spontaneity, and that is what we will come back to or start at in our next video.